Another type of two-dimensional motion that I want to talk about in this chapter is circular motion. Uniform circular motion, specifically. So, let's imagine that I'm winging a ball around my head on a string. And let's say that it's moving at a constant speed. So, here's a sort of a top view of what I'm doing. And just to pick a number, let's say that it's going 10 meters per second right here. And then right here, it's going still 10 meters per second. And to add to the excitement, over here, it's also going 10 meters per second. Okay, so this one's a little short maybe. Okay, there we go. 10 meters per second everywhere. Top view. Kind of like what I have here in the PowerPoint. Question is this ball accelerating? What do you think about that for a second? Well, remember what acceleration is. Acceleration is a change in velocity. And remember that velocity is speed and direction. Velocity is a vector. It has a magnitude, speed, and it has a direction. Okay, so is the speed changing? No. Is the direction changing? Yes. If the direction's changing, then is it accelerating? Well, these aging rockers think so, and they are correct. The ball is accelerating. Remember, acceleration is speeding up, slowing down, or turning. So, it turns out that this kind of acceleration has a very special name. We call it the centripetal acceleration, and it always points towards the center of the circle. In fact, this word centripetal, it means center-seeking. So the centripetal acceleration always points towards the center of the circle. And we're going to see that as we go along. An acceleration and a velocity that are in the same direction is an object that is speeding up. An acceleration and velocity that are in opposite directions, well, that's an object that's slowing down. A velocity and an acceleration that are perpendicular to each other, that is an object that is turning a corner. Okay, so the centripetal acceleration always points towards the center of the circle. Since there's a 90-degree angle between the velocity and the acceleration, this is an acceleration that is changing the object's direction, but not changing its speed. So it is pointing towards the center of the circle. We call it centripetal, which means center-seeking. And we have a fairly straightforward equation for it. The centripetal acceleration is given by v squared over r, and it always points towards the center of the circle. It's not too bad. Let's do an example. Again, we're going to read it quickly, let it flow over us. So turning a corner in a typical large intersection in a city means driving your car through a circular arc with a radius of about 25 meters. If the maximum advisable acceleration on your vehicle through a turn on wet pavement is 0.4 times the free fall acceleration, what is the maximum speed at which you should turn? Okay, well, this is a fairly straightforward application of the centripetal acceleration equation. So we have a sub c equals v squared over r. Well, what's been given? Do we know r? We do know r. R equals 25 meters. How about v? Do we know v? We don't. In fact, that's what it's asking for. How about a? We do know a. It's kind of a goofy way that they told us. It says what? It says it's 0.4 times the free fall acceleration. What does that mean? It means 0.4 g's. And so we should write this as 0.4 times g. Okay. So we're looking for v. We just need to do a little bit of algebra. First, I'm going to multiply both sides by r. And I get. And so, of course, next I take the square root. So I get v equals the square root of a sub c times r. Which equals, so I'll plug in my numbers here. Run my calculator, and I get 9.9 meters per second. 9.9 meters per second. That's something like 22 miles an hour. say that's reasonable for the fastest you should possibly take a corner in a city on wet pavement. I like it.